Virtual commissioning, the next step in advanced manufacturing. As I mentioned a moment ago, we are joined today by Steve Cardozo, Engineering Manager at InCycle Automation, and Ethan Tellis, Solutions Consultant at Siemens Digital Industries Software. Here's a quick agenda for today. We're going to run through an introduction. I'm just going to give a high-level introduction, followed by Ethan Tellis, who will take over and welcome you to the world of virtual commissioning, followed by some success stories and real-world applications from Steve Cardozo at InCycle Automation, which will be followed by our Q&A. And so here's a quick introduction to digital twinning solutions, which is pretty much the umbrella term you could use for a lot of the things we're looking at today. But first, I want to just say a little bit about long-term technology services. Our mission is to be your trusted partner for exploring new digital solutions that are going to lower your cost, lower your lead time, increase your production quality and efficiency, and at the end of the day, make your company more profitable and competitive. And we're really doing this at two levels. First, you've got that more long-term level that's helping you build a common digital thread through a number of solutions that can span your product design and your product engineering all the way to your production scheduling, plant management, and what's most relevant for today's webinar, your machine and line commissioning. But we also know that it's our mission to meet companies where they are, especially small to medium-sized companies. So in other words, if there's anything you see in this webinar that seems like, it would just require too much upfront investment of time, internal expertise, money, please just know that at Long-Term Technology Services, at LTS, it's our responsibility to create situations that work for you. It's up to us to really find those situations that give you clear proof of concept, really strong ROI, and most importantly to a lot of people, a compressed payback schedule. I've got a cousin who's a CEO at a company here in Ontario, and he likes to always tell me, Phil, if I'm not getting my money back in 2 years, it ain't going to happen. So we like to address this through a combination of software solutions, training, and consulting that's really tailored to your exact needs. Before I begin here, I want to just say, be sure to join us for our next webinar, which is going to be leading the way in simulation-driven machine and line design. So we're going to be talking about the level of designing the individual machine and mechatronics concept design. For that one, we'll be joined by global experts Bernd Mussmann, who's going to join us from Germany, and Xiaojiang Shi, who will join us from Irvine, California. Today, we're going to be talking about how the digital twin can help you generate PLC code and validate your programming in a virtual setting with virtual commissioning. So with that, let's take a look at some key trends. As many of you know, there's a number of trends that are forcing companies to become leaner, smarter, and more agile, while somehow increasing the quality of their products. And some of these trends are what you see listed here, like consumer-driven customization, smart machines, hyper-automation, and global competition and new business models. And at the end of the day, customers are looking for things that are more personalized, flexible, faster, and better quality, basically wanting it all. It's our belief that the holistic digital twin is the way to meet these trends and their accompanying demands. So what do we mean by that? Well, if you think of traditional simulation, you're usually thinking of a geometric kinematic simulation that's pretty hypothetical, pretty theoretical in nature. It's not really the reality. But a digital twin is a virtual replica of your product or machine that really gets into those realms of electrical, engineering, mechatronic, thermal transfer, you can name it, and it uses physics-based modeling. But what's most important for this webinar today is that these simulations can use real controllers to drive simulations that run real PLC code, which you're able to validate and export from a virtual setting. So now what you're talking about is a type of simulation that truly offers a stand-in for a real device or production line that can also be connected to that device or line in real time. And as we're going to find out today, especially from Steve and his real-world application, that has big implications for the way we do things in manufacturing. It's this approach that allows you to bring more of your manufacturing and automation concerns into the design and engineering stages of your product lifecycle. And so basically you can perform more work than ever before in a virtual setting with total confidence that when it comes time to manufacture or commission a product, you can do it error-free and save a lot of time and money in the process because you're not tinkering around with the real machine and kind of waiting for collisions to happen. I remember a case study from somebody in Germany saying, we had way more collisions this year than ever before, and we couldn't be happier because they all happened in a virtual setting and allowed them to tackle bolder designs. So once you've decided to go down this road of digital twin technology, then you're looking at a question of scope. And digital twin technology runs all the way from plant level simulation, which we saw in the first of our next step webinars, down to the level of the production line, robotic work cells, or even a robot station or individual machine. And for this webinar, we're really going to focus on the robotic station and the line, but we're also going to bring it all the way down to that bottom level you see, which is automation, where you're looking at virtual PLC and HMI simulation. And so with that, I would like to turn things over to Jeethan Tellis to bring us some more knowledge about virtual commissioning and what it can do for you. So over to you, Jeethan.
Thank you, Philip. Let me go ahead and share my screen. Philip, just to confirm, I'm sharing right screen. Can you see my screen?
Yes.
Thank you. Okay, so before we go into virtual commissioning, let's look at the typical challenges faced by the line builder, automation companies, and OEM during design and production phase. We should be validating cell component design much earlier in the simulation environment. That could be a fixtures or jigs, performing different robot simulation with the robot specific syntax, programming it in precise ways so that it's reachable first. There is no collision in the path. Third, we want to ensure the build quality of our cell, what we are building. And finally, next, we want to ensure we are meeting a customer requirement, that is a throughput, by minimizing the cycle time. And then we lean on to the next area, which is automation and control area, where we validate safety as well as other interlocks inside the cell, other control aspect, how we are controlling the cell. Such high complexity requires usually a dedicated tool for individual challenges that we see on the screen. This is where a Siemens OLP and simulation tools are critical today for our application, which serves as a single platform to cater all this requirement in single environment. Now, typically when we look at the robot cost, the major chunk of the cost goes into the software and programming. We may think of hardware cost is high, but in reality, based on the research, it's the software. So the software cost is not upfront. It might be spread over the period over the period of life cycle. It could be starting with robot software and programming completely till the emergency control. So we are going to spend lots of we are going to invest lots of amount. So how do we reduce this? The solution strategy that we can use is to utilize one simulation environment to plan and validate robotic and automation aspect throughout the entire workflow, starting right from the, we can say, process definition all the way till virtual commissioning. At this point, you may ask, why do we need virtual commissioning? Is it really required? So in this slide, I'm going to explain why we need virtual commissioning. Traditionally, when we look at the manufacturing process, we first focus on detail engineering phase, where all the departments are working in silos, they are serialized. This has the issues. The commissioning is taken up at the end, real commissioning. There are three key challenges. One, the serialization takes up much time. Each department is dependent on other. Second, the virtual commissioning is usually performed by an expert on site. Physically, he has to travel to the site and he has to spend time. Finally, when all this is going on, we are accumulating the cost of idle inventory as well as resources. So what's the solution for this? First is we want to parallelize, or we want to use shift left approach, where each department can parallelly start working. With this, at the end of detail engineering phase, we have a complete digital twin. With this digital twin, we can leverage and go ahead and virtually commission before real commissioning. The problem discovered at this point can be taken up in digital twin itself, and we can solve the issues or errors, whatever is coming up in the digital twin, so that we can save time and effort in tremendous way. So today's focus, we will utilize one simulation platform to carry out signal-based simulation. We will see different techniques of virtual commissioning, such as hardware in the loop, software in the loop, which I'll be speaking in the next slides. Finally, we will see how you can collaborate smartly to review virtually commissioned cell or line in virtual reality world. So with that, let's go to a signal-based simulation. We have a cyclic event evaluator which supports the signal-based simulation. Now, why we need signal-based simulation? Signal-based simulation allows a simulation to continue running repeated cycle, much like a production system. Now we can analyze the process sequence and robotics which are joined, finally enabling engineer to validate robotic and programming and overall system behavior at this point. Here in this example, what we are going to see is a welding station of two parts, welding station for two car parts, and then we'll see how to verify signal communication between the cell component, finally come up with the right OLP code for the robot. Let me go ahead and play. As we can see, this is a spot welding cell. We have a simulation monitor through which we are interfacing, we are controlling the cell parameter. It's not driven through the time-based simulation where we'll have Gantt chart where we'll fail to repeat cycle. Instead, we are controlling the simulation through the signals accurately as we are controlling in the shop floor. At this point, we can go ahead and select the right OLP code which is required to run the simulation. Like for example, we can select different paths here for robot and select if there is a variant which is introduced during the production, how we can take up that. So we want to verify those aspects in signal-based communication in the virtual world. So here we can select right process. We can with the just by click we can select the right OLP code required for that specific robot, which will be communicating in closed loop fashion with the signals. We can select right options for the code and verify the right code is being applied. Once we have that, we can go ahead and simulate, still control through a simulation panel all the aspects of robotics here. Here now we can see spot welding is going on. The first part will go to PED welding. Here we can see a PED welding station where the PED welding takes place. The second part, second variant, we can bypass the PED welding. For second part, we don't need a PED welding. We can verify that aspects in the virtual environment. As we can see, the second part, there is a bypass for the PED weld. It is directly gone to the conveyor. Also, we want to verify how the individual actuation is working. For example, the gripper is, suppose gripper is closed after the cycle is completed, and in reality it has to be open. If there is a jam, how do we overcome that? How do we verify that? Here we can see the robot gripper is jammed, and the simulation, as you can see, when the robot is going to pick, it's going to give error, it's not going to pick. We can go ahead and take out that, zero down to that issue, and once we zero down to that error, we can rectify the code. Here we are ensuring again signal-based communication is working, and this forms the base for the virtual commissioning. So you can see the cell now, it is fine-tuned and it's working smoothly. compared to before. Okay, with that, signal-based simulation replicates repeated cycle much like a production system. The main advantage here is we can validate signals communication, detect any faults which are happening, and correct the fault, most important. And this serves as a base for the virtual commissioning. In this example, I'm going to show you hardware in the loop. So why do we need hardware in the loop? The advantage with the hardware in the loop, or the why we need hardware in the loop, the reason is the same hardware is going to sit in the shop floor. It could be PLC or it could be HMI, it could be any brand. We can connect that hardware to a virtual environment. Virtual environment, it could be a virtual environment of the cell which is there in our laptop. We can connect that hardware and drive exactly similar to how we drive the cell in the shop floor. Now, just to give you a bit more explanation on the hardware in the loop, how it works, we have a digital twin of the cell in our system or laptop, which includes robotics, equipment, as well as the material flow. To this, we can connect to a real hardware, in this case, S7-1500 PLC, Siemens PLC, and HMI. We can take any PLC, any brand, and connect as far as it is OPC compatible. Now, this connection is established through OPC communication protocol. We can also connect the field devices through a SIMIT interface to the process simulate and drive the simulation. In this example, this is a video I recorded for our webinar. Here you can see in this, what we are going to see is real hardware, S7-1500 hardware, and S7-1500 hardware and HMI controlling the simulation. Let me go ahead and play the simulation. The simulation is for, here you can see the hardware and which is connected to the cell. The cell has 3 robots, 1 pick and place, and 2 robots are for welding. Now, at this point, we can initialize. As soon as I initialize, only conveyor is initialized. We want to go ahead and start the PLC here. As soon as I hit start here, as you can see, the lift on the cell, lift in the cell starts moving, delivering the part from the previous cell. As soon as it reaches, it's in auto cycle, as soon as it reaches a particular location, robot gets the signal, pick and place robot gets a signal, it picks up that specific part and places it on the indexing table. Once the part is placed, there's a confirmation, robot goes to a home position and the table is indexed. Once this table is indexed, the spot welding robots gets the signal that part is in place. Now it will carry out spot welding operation. And the second cycle parallelly continues, where the second part is delivered, robot goes and picks up the second part, loads it onto the other side of the indexing table. Once that is loaded, and first part is finished now, it's indexed back. The robot, pick and place robot, picks up that finished part and puts it onto the conveyor. So all this process is happening through a exact PLC code that will go onto the shop floor. And we are driving this, as you can see, with a HMI and a PLC, which is controlling all the aspects of simulation here. The other cycle continues. The advantage here is that we can continue to produce multiple parts and verify at what time there is an issue, or at what part, after what part there is an issue. We can detect those issues. At this point, if you want to interrupt, we can have the interruption. We can pause the simulation and verify other aspects, maybe a manual operation. For example, if the part is stuck, how do we retrieve it? So what's the advantage of having hardware in the loop? We can connect a real hardware to a digital twin and drive that digital twin through a real code which goes into the shop floor. We can have multiple PLC vendors and those PLCs we can connect to simulation environment and drive the simulation. Next, I'm going to talk about the virtual commissioning in software in the loop. When we say software in the loop, we actually want to virtualize the PLC part also. That means we can carry now a digital twin of the cell in the laptop as well as the virtual PLC in the same laptop or emulation software in the same laptop. So just to give you a quick rundown, we have a digital twin in the in our system, which includes robotic equipment and material flow as before. But the changes here, instead of having a real PLC, we have a virtual PLC, which will communicate with the cell directly, PLC and HMI, which can communicate directly to the process simulate and drive the simulation. In next example, we will see how we can drive AGV to commission it using virtual software in the loop. Here we are using PLC Sim Advanced in the background as a virtual PLC, as well as a HMI, which you can see on the screen. Let me go ahead and play here. Initially, we want to select right AGV for our application. There are multiple AGVs and multiple routes here. We want to pick a specific AGV, and we want to call that AGV to an assembly station to pick up the part. Here we are controlling the AGV in, as we can see, in a HMI through our virtual PLC. AGV has reached specific location. We want to verify the lift here, pick and place robot, which can pick the right tray and place the right tray back. Now, at this point, the lift robot, what happens is when we call for the second time, it is supposed to go up, but as we can see, the lift has not gone up. Let's see whether AGV will detect, or our program will detect that. Yes, we can see the AGV is stopped and there's no collision. At this point, we can go to a manual screen, check what is the issue, manually go and override it, manually make the lift to go to the home position so that AGV can occupy the predefined location. Once we have AGV at the particular location, we can go to a PLC and modify that code. In this case, automation portal, programming portal, wherein we can add other logic blocks to confirm that the lift has gone to the home position, and load back that code, finally test that whether it is taken care or no. This is all happening in virtual world. Even if there's a collision, there's no issues. If it happens in real life, it would cost us much. With that, having a software in the loop or virtual PLC enables us to fast forward the simulation. For example, we can take the simulation and run it for few hours of simulation. We can run it in few minutes. One. Second, we need not have the hardware right next to the laptop, which is hectic to carry when we go to customer place or when we are working on multiple projects. Finally, I want to, now we have a digital twin which is virtually commissioned. Here we will see how we can take this digital twin into the virtual reality world and review the cell with the stakeholders. In this example, again, we have a HMI controlling the cell aspect, the similar cell which I showed you in the hardware in the loop. We will verify how it is happening, and we can immerse ourselves inside the cell, walk through the cell. These are the 3 points. Let me go ahead and play the simulation. With a click of a button, we can navigate inside the virtual reality world. Once we are in the virtual reality world, we can select the right WinCCC or HMI screen for our application, circulate between a different screen and select the right one. At this point, you may want to position right next to cells from where you can view the all aspects of the cell, how it is working. Right? This is the right position. We can pull out our HMI screen. Now, this is controlled by a virtual PLC in the back end. That's a PLC Sim Advanced, which is controlling this, which is also connected to a HMI here. Once we have the screen in the right position, we can initiate the simulation and start the simulation. Now, the simulation is driven by a PLC code. Once we hit the simulation, the part starts moving in. We can go navigate or teleport ourselves right next to the robot or over the robot, which is not really possible in real world. That using virtual reality as a smart review tool for internal as well as a customer review, we can leverage one platform for all this application, which in turn reduces the cost and risk of traveling and training also. We can carry out training also with this solution. In a nutshell, what we have seen is by using a virtually commissioning capability, how you can reduce production risk, ensure cycle time, save engineering cost and effort, avoid equipment damages, shorten commissioning time with the shift left approach, and finally, validate multiple scenarios in virtual world. With this, I would like to thank you, and I will hand over the session to Philip. Philip, over to you.
Thank you very much, Ethan. And with that, I'm going to pass things over now to Steve Cardozo, the engineering manager at InCycle Automation. And Steve's going to take us through some examples of some of the things he's been doing with Process Simulate and his real-world application of it. Steve, over to you.